All right, line W1, learning task 8. We're going to go and take a look at the operation of my AC motors when used with variable frequency drives. And the motors that we're going to be talking about are going to be our standard three-phase squirrel induction motors themselves. Those squirrel cage induction motors are going to go and have the stator that we've talked about before that's got the 3 windings, 3, 6, 9, or 12 windings actually, that are going to be connected in delta Y, and that just creates a rotating magnetic field. And then that rotating magnetic field that we have going around the stator is then going to cut across to the rotor, where it is going to go and magnetize and create current flow inside of the rotor bars, which is then going to cause the rotor to go and catch up and follow this. We know that ultimately it's the speed of our synchronous field is going to be related directly to the frequency that we are going to go and operate these at. We've got a formula for this. If you go back to your ITA formula chart, you should recognize it right here on the bottom. I'll just go to it. Over here, we see that we have got N, which is going to be my speed. N is going to be equal to either my pole pairs or my pairs, whichever it is going to be, but it's going to be 60 times my frequency divided by my pairs of poles. That's going to go and determine what my value of speed is going to go and be. If I take that one back onto this one over here, 60F over P, let's write that one down. If I see that I start to go and vary my frequency as I have got a fixed motor, motor's going to go and have only a certain number of pole pairs, but let's say that we've got a motor that's got one pole pair, what I can do then is I can go and vary my frequency all the way from 0.6 of a hertz, let's say, all the way up to 90 hertz, and as I would go and increase that, what we would see is that my speed that motor is going to be outputting is going to go and change as well. So it's all to do with the frequency, how quickly we are going to be rotating this motor, spinning that rotor around. The torque of the motor is going to be dependent upon whether or not we can go and maintain that constant VF ratio, volts to frequency ratio, right? We know that we've got a formula that's going to go and govern that. T is equal to K phi I of my rotor multiplied by my cos theta that I'm going to go and have. All of that is going to be tied together, and we know that we have got our volts that are going to go and control the frequency, or sorry, the flux that I'm going to go and have mostly, and we know that we are going to go and have my rotor current that's going to be mostly controlled by my frequency. So we have to maintain that so that these two stay in the same ratio so that we maintain torque off of the motor itself. As we go and speed the motor up and down, we also have got a couple of other, more physical things that are going to go and happen. One of the big things that happen is any attached cooling devices that we have, fans on our totally enclosed fan cooled, are going to be slowed down. Therefore, we are not going to be able to maintain the same amount of cooling that we are going to go and have. As a result, we do have to go and watch the types of motors that we are going to be using. Generally speaking, if I'm using a three-phase motor, or if I'm using a VFD, I've got a couple of things that I need to be aware of. First of all, since cooling is reduced, I might have to go and use a larger frame. A larger frame just means that there's going to be more surface area which it's going to be able to effectively dissipate heat with. I might have to go and provide external cooling, where I'm going to go and provide some sort of a blower that's going to go and provide air over top of this. Doesn't have to be much, a little quarter-horse motor or something like that. That's just going to run a blower fan to keep everything cooled down. And if my motor is running continuously at low speeds, below what it's rated, below 50, 60% and below, I have to reduce the amount of torque demand that I'm trying to go and pull off of the motor itself. It just has a harder time to maintain that, as well as we've got longer, slower peaks, right? If you take a look at a regular AC sine wave, that's going to be this thing at 60 hertz. If it's going to be at 30 hertz, now I'm going to go and have twice as long. And if I take a look at the length of time that I'm at a peak, where I'm at a peak value of voltage, which means I'm going to be running a peak value of current through those motor windings, I see that this has gone and increased. So if I'm going to be running at a super low frequency, I have to go and upsize my motor so that I don't cook off the windings, because I'm running a peak amount of voltage and peak amount of current for longer periods of time. We also have got, anytime that we are working with these motors, we talked about inverter duty before. Inverter duty is also oftentimes going to go and require us to have larger circular mill area, just because we have got these more rapidly rising, especially PWM type of waveforms. We're going to go and have more rapidly rising front edges, which means that we're going to go have more skin effect, where we're driving the electrons out towards the outside edge and getting less that's going to be carried across the center of these ones. Torque characteristics of these motors are going to be consistent, provided that I go and maintain that VF ratio over here. And what we see is, I'm maintaining that this is what the motor is rated for, 460 volts, 60 hertz, and that I'm going to go and have at that a certain amount of speed that it's going to be rated for, 1800 RPM, which would be its synchronous speed. And obviously I'm going to go and have some sort of a slip that's going to go and happen between the 1800 down to where this thing is actually going to be operating, right? So I'm operating a bit below 1800, but I would see that I'm going to go and have my peak of my torque that is going to be maintained because I've got my volt frequency. As long as I scale my volts and frequency together, I'm going to be able to go and maintain that peak always at a little bit behind my rated amount of speed that I'm going to go and have at each of those different values of frequency. We're just taking the whole waveform. This is not like when we were looking at the wound rotor motor where we were stretching. This is now physically shifting. It's the identical wave. It's not stretched. It's just shifted over every single time as we run through these. Once again, this is going to be a limited amount. Now, if I've got a 480 volt motor and a 480 volt drive, I'm going to be able to put out up to 480 volts. And I can then, using my drive, drop those values down to these as I'm dropping my volts and my hertz through each of these. If, however, I want to go above that 60 hertz, once again, if I increase my frequency above rated frequency, above the 60 over here, I'm no longer going to be able to increase the voltage because we aren't putting in more than that 460 volts. Therefore, I would not be able to go and operate this motor any faster. I'm not going to be able to go and run this thing, I can operate it faster, but I'm not going to be able to establish proper torque as I am doing so. Braking of these, braking of any type of a motor is going to be automatic when we look at regeneration, right? Dynamic braking was where we were going to go and take a motor, we were going to go and use the inertia of the rotor as our prime mover, and we were going to go and turn the thing back into a generator, so to speak, and dissipate power across a load. Regenerative braking is where we are going to go and push that power back out into our circuit. Now, when we took a look at the inverters that we had earlier, we saw that anytime that we are collapsing those lines of flux, and when we were looking at those H type of bridge inverters, we saw that anytime we were collapsing those lines of flux, we're able to go and drive back through those diodes on the system back into my main buses. And because we are going to go and put it back onto the DC, it's actually really, really simple for us to go and do regeneration. They give us this curve over here. I'm going to move the curve over to the side. We're just going to talk quickly about that DC bus system. When we were looking at the DC busing system, we'll just go and draw a single load across in between two of these. And then we saw that what we can do is we can then go and have, so these are going to be my control SCRs over here, that I can then go have another set that is going to go and allow me to dissipate out from each one of these ones. Once again, we're going to go and put these in opposition. If this is going to be my positive line over here, I'm going to go and put this one in opposition to that one. This one over here is going to be in opposition to its negative line. So we see that they're lined up over here because that's going to be my negative bus. This is my positive bus over here. And same with these ones over here and over here. All that this allows us to go and do is this allows us to now utilize each one of these to go and kick out those values of voltage, to kick those things back out onto my DC bus every time that we would go and collapse, because normally we're going to have current flow. Let's say that we have got current flow that is going through, sorry, this one here is backwards. I keep drawing this thing backwards, but that's okay. That's much better. Like that. Okay. So now when we have got current flow that is going through, and this current flow is coming from usually our inductor collapsing field or a cap. Remember the VSI and the CSI types of drives are going to be filtering, meaning we're rectifying in, but then we're storing some energy inside of that cap and that inductor to give us that ride through. So normally I'm going to have current that's going to be going through like that. And then every time that I shut off my main current, I'm going to go and have that inductor trying to maintain current flow through there, which means it's going to turn into a source, which means it's going to have a positive here and a negative here, which would mean that it would then be able to go and drive its positive as a source. It is then going to be able to go and take current and collapse its lines of flux back in. It's going to be able to send some negative back into the negative. It would be able to go and send some positive back into the positive. And so those collapsing flux lines coming off of my individual windings are going to get fed back into the DC bus, where they will enable us to maintain that DC bus voltage. They do have a whole pile of different points that they have on this graph over here to kind of explain the exact same thing. This one just shows it as, operating points. What they're showing is they've got a motor operating, same motor that they've had, all these other times, 480 volt motor that is operating at 60 hertz. It is normally going to be operating right over here at 100% torque. But then if all of a sudden I decide that I'm going to go and switch from the 60 hertz down to 30 hertz, so I want to cut my motor speed in half, what happens then is instantaneously my drive is going to go and slow its roll as far as how it's chopping up and sending out voltages off of here. So that means that my synchronous field on my motor is going to go and drop all the way down. If this over here was going to be a synchronous speed of 1800 for me to be operating over there, now I'm going to drop from 1800 down to 900. That's going to be what it's going to call for at 30 hertz. When I drop that thing down to 900, what actually happens is my rotor itself, we're operating right about here, about 1700-ish. So now my rotor is spinning faster at this point. As I transition, my rotor is spinning faster, and then what my field is itself. So we're going to go and have a braking sort of effect that's going to be generated off of it. That braking effect is going to be this curve over here that we are going to see. We are going to be braking all the way through until here, where my motor, anything from here to here, is my motor running faster than my synchronous speed. And then my motor slips back into its regular operation. Then it's going slower, and then at this point, that's as slow as the synchronous field is going to allow this thing to go and operate, and then it picks up, and that's where it's going to go and run at now, based on those RPMs that we are going to have. This motor, when it slows down like that, if it's going to be a rapid slowdown, we can go and have a very large amount of current that we are going to go and regenerate and try to send back in. In some cases, we're going to actually have to go and divert it. Then we're going to have resistance that's going to be connected across the DC bus that is going to be able to burn some of that off if we're not able to actually put it back in rapidly enough. But most of these times, they're going to be able to go and place this or to take this all back in on the DC bus. There's usually room in either the expanded magnetic fields around the inductor in the case of a CSI, or in the plates of the capacitor in the case of a VSI drive for us to go and do so. In other cases, what we could also do if we're actually trying to brake, and instead of just regenerative braking where we're moving down from one speed down to another, the other option that a drive can do is that the drive can actually just go into a form of injection braking, where we're just going to go and for this specific winding, I would just turn this one on constantly and this one on constantly over here. And what that would do is that would now provide a fixed field. Basically, it would lock my fields that are usually whipping around the stator. Now what we would do is we would just freeze them in place. So we're going to have 3 individual fields around there, which means that that inertia that's driving the rotor through there is going to go and cause us to burn off heat across the rotor that we are going to go and have. This would be something that you can just program into the drive. The drives are not usually going to go and have this by default because, as we know, DC injection braking does usually cause us to go and overheat the rotors, particularly if they're going to be done a lot. Reversing of AC motors attached to these drives, we don't have to interchange any lines. The drive itself is just going to go and change the sequence that it is going to go and run that in. In a lot of cases on our drives themselves, they're just going to go and have a low voltage bus. So we're going to go and have, our 3 main terminals that are going to be at the bottom, UVW, as well as our line 1, line 2, line 3. That we are going to have, those are going to be the main ones. But then up above that, there's usually going to be this small little bus that's going to be all done with control driver types of screws that are only 1 or 2 mil across. That bus over there is usually going to have a positive voltage that is going to be taken off of the inside that we're able to go and run to the outside. This is where we're going to go and get all of our control power off of. Just erase those over there. And then I'm going to go and take each of my individual components back in. My stops are going to come into there. My starts are going to come into there. And I'm also going to go and have, in a lot of cases, here's my start, here's my stop. I'm going to go and use a selector switch that I can then go and drive into one of these that will select whether this thing is going to be operating in forward and reverse. You know, when the switch sits open, it's operating forward. Whenever the switch is enabled and it's closed, then we would be operating in reverse. These motors are motors when they run off the VFDs. We can go and plug them to a stop. We can control the amount of plugging, the amount of current that we're going to be letting through with the SCRs. We can basically decelerate them down and then accelerate them back up in the opposite direction. As far as protection on our motor, once again, we need to go and have a motor that is going to have a high insulation class rating. Usually we want to see like insulation class as far as temperature, that's going to be pushing up towards the H type of level. We also want to make sure that these things are rated for that inverter duty, which means that they're going to have oversized windings, magnetically braced, etc. Those windings do have to be capable of withstanding those high voltage spikes. That's that reflected wave that we talked about before as well. And we do protect our motors by programming them into the drive itself. That whole programming of what the motor current and horsepower is very critical, because that's what my system uses to go and tell then, excuse me, to go and tell when we are running into an overload. It's just continuously monitoring the current that we're sending out. And so if we've got it programmed properly, it recognizes when we've had too much current for too long, and it'll shut us down on that overload. All right, we are going to move on to one of the most useful motor sections that you are going to go and have for the year, which is going to be connecting variable frequency AC drives.